And welcome everyone. Let me make sure that you are seeing my screen and we'll get started. I've got the top of the hour here, and so we're going to be talking about design of load-bearing tall wood studs for wind and gravity loads, and Lori Cook will be joining me a little bit later on in the program. You should have already seen the description and learning objectives when you registered, so we won't spend any more time on that. We do provide AIA credits for our participants. So this first one will kind of get you a sense of how the poll questions work. So I'll have Marcy come back and launch this first poll, and you can respond so we'll get a sense of who's here today.
Absolutely. Go ahead and tell us what your profession is. And as a reminder, please vote in the blue box. Do not vote anywhere else. Just vote in the blue box for us, please. So, and I'll give you about 30 seconds, and 80% of you or more. All right, so I'm going to go ahead and close the poll and then share it. Let's see, we've got about 79% engineers, 11% code officials, 5% architect building designers, and 4% other. We are so glad that all of you are with us, and welcome.
Yes, welcome, and that looks like a pretty typical audience turnout for us in these webinars. So what we want to do today, as far as a course outline, is share a little background on design loads that we'll be talking about in the example problem, wind and gravity design loads. We'll take a look briefly at the engineered and prescriptive provisions of the wood frame construction manual, and then jump into our design example. And because I got beat up pretty good last time about going too slow through the background, I'll fly through this, and I'll probably get beat up today about going too fast through the background, but that's okay. Here are the resources that are available as we talk through this program today. Many of these are available to download free or free view only from our website. The wood frame construction manual is adopted in a residential code and the building code, and the latest version is the 2015 wood frame construction manual is in the 2015 IRC and 2015 IBC. The codes and the wood frame construction manual all reference ASCE 710 loads, so we'll be talking about ASCE 710 wind loads and gravity loads as we look at the example problem. So first I want to jump to the commentary. You won't be able to download this from the website, but we excerpted a couple of pages here from the commentary to give you a sense of the background, the loads and the assumptions that we make in the wood frame construction manual. So again, everything's from ASCE 710. Our wind loads assume a box-like structure. We assume enclosed structures, so you'll need to make sure that you are protecting openings to avoid breach of the structure, because we assume an enclosed structure for all wind analysis. We are using the ultimate loads adjusted down to an allowable stress level, and we'll be looking at both main wind force resisting system loads via the envelope procedure and component and cladding loads, or CNC loads, per ASCE 710, and you see some of the equations and references to ASCE 710. So when we talk about ASD velocity pressures, here's an example of a velocity pressure calculated for 150 miles per hour, exposure B, and adjusted by that 0.6 factor that you see there on the screen that gets you to an ASD, allowable stress design level. So this would be a velocity pressure at 150 mile per hour, exposure B, a little over 21 pounds per square foot. So again, that takes into account the 0.6 factor that you're going to see a little bit later on in some of the load combinations. We've already taken that adjustment in what we'll be looking at. So if you don't see that 0.6 show up in a load combination, it's because we've already taken it into account here. For uplift loads, we are deducting for dead load, and so that gets accounted for in the load combinations as well, and you can take about 60% of the dead load to offset your uplift. For snow loads, we are looking at both balanced and unbalanced snow load conditions in the design process, so we'll look at both of those in the example problem. We account for that in the wood frame construction manual analysis. We do not account for sliding snow. That's outside the scope of this document. So if you're in an area where that's a case, a big deal, then that will have to be done separate from this analysis. And again, we do assume protection of openings. So our calculations assume a fully enclosed building envelope and that it's not breached. So into the wood frame construction manual then to find out if you can even use the manual, and there are tables at the beginning of each of the chapters that give you a sense of that. We're going to be looking at roof ceiling assembly dead loads of 0 to 25 pounds per square foot in the document, roof live loads of 20 pounds per square foot, ground snow loads up to 70 pounds per square foot, and wind loads up to 195 miles per hour. So we have selected some specific loads from this range for our example problem that we'll be looking at today. So we know that we can use the wood frame construction manual for parts of this analysis as well, and we'll show you where that is. So jump into Table 2, which is the front end of Chapter 2 in the wood frame construction manual. This table gives you a sense of whether you can use the engineering provisions of the wood frame construction manual. And notice that there is a difference that I'll point out in a second between the load-bearing wall height. In Chapter 2, we can go up to 20 feet, and our example today will go up to 20 feet, or 19 feet actually. And the non-load-bearing wall height is also 20 feet. So from an engineering perspective, you can design both load-bearing and non-load-bearing walls up to 20 feet. Our lumber rafter spans, I-joist spans, roof truss spans are limited to 26 feet and 60 feet for trusses. A lot of that has to do with just the capacity of the double top plate and making sure you don't exceed the capacity of the double top plate, and we don't exceed those span ranges for the example we'll be looking at today. So we get into the enabling language in Chapter 2, and here's where the text says, okay, for exterior wall studs in Section 2.4.1.1, you're going to use Table 2.9a or Table 2.10, and then for load-bearing studs, exterior wall studs, I'm sorry, that's for wind loads, 2.9a or 2.10, and then for your gravity loads, 2.9b or 2.11. And then we'll look at those chapters, but I want to make sure you understand the text here that gives the enabling language for those tables and how they're to be designed. Then here's a list of tables we'll look at briefly. It's kind of a table of contents for the tables that are in the engineered provisions of the wood frame construction manual, so you can get a sense for what's there. Table 2.1 is lateral framing connection loads from wind, and we'll use these CNC loads in the analysis so you can see where those come from. I've highlighted one here, 148 pounds per linear foot for 150 mile per hour wind load. And then note the footnotes say this is for an exposure B, mean roof height of 33 feet. You can adjust for other wind exposures, C and D, and other roof heights per table in the wood frame construction manual. You also have to adjust for your spacing of your components. In this case, studs, if they're at 16 inches on center, would be bumped up by a 1.33 factor. So let's see how we come up with that value of 148 pounds per linear foot. We're going to use component and cladding loads on the tributary area for that wall system, and When we do that, we make some assumptions about a minimum required area for the analysis, that h squared over 3 is what ends up being that minimum requirement. We run through the calculations, and you can see over here on the right-hand column we come up with 148 pounds per linear foot. So the reason we show this commentary here for each of these tables is so you don't get the impression that this is just some black box. We show an example for each of the tables to show where we get the numbers from ASCE 7 or whatever calculation we're doing, so that you know what the background calculations are. And again, if we're at 16 inches on center, you'd bump that 148 pounds up to just shy of 200 pounds per connection. So at the top of the stud, the bottom of the stud, that's the load on those studs, but that also gives you a sense of what the loads, CNC loads on those studs are. We're doing end zone coefficients. Those are much more conservative at the corners, so we've given some footnotes that allow you to calculate for interior zones, which have a little bit lower wind load, and so you can adjust those by a factor of 0.92 to come up with your interior zone loads. So we jump to table 2.9a, which is the exterior wall stud bending stresses. So we calculate moments in the next table, but this will give you a sense of what the bending stresses are on exterior wall studs. And for this particular commentary example we're going to look at, it's 150 miles per hour, 2x4, 10-foot wall height, 16 inches on center, comes up with a value of 1820 psi. So that's your induced F sub B, or your little FB, and when you would compare that to your allowable bending design value, FB prime, you could make a quick determination about whether those studs work for those CNC loads. And again, the commentary here gives you a sense of how we calculate those CNC loads for exterior wall studs. And what we've talked about in previous webinars and what we'll reinforce today is that for all the studs that we tabulate or calculate in the wood frame construction manual within the limits of this manual, the CNC bending loads on the studs will control over the main wind force loads combined with axial loads. Okay? So you're going to check both CNC bending only, then we're going to check main wind force in combination with gravity, and what we're going to find, even with the example today, is that CNC bending loads control because they're such much higher magnitude than the main wind force loads. And there's a paper, a link to a paper here that shows you a little more background on that. We've updated and published a new paper recently based on this webinar as well that'll be out pretty soon. So you see the 1820 psi and how we calculate that. We actually have to jump to the next table to get that moment that we use there. So table 210 then gives you your exterior wall induced moments from wind loads. In this case, again, 150 miles per hour, 10-foot stud at 16 inches on center. We have an induced moment of 465 foot-pounds on that stud. And we jump to the commentary, which we've excerpted here. We're using our CNC loads to come up with that moment of 466 foot-pounds. So there's some rounding differences that you'll see between what we calculate here and the table, just so you're aware. All right, then we're going to jump to gravity loads. Table 2.9b gives us our exterior wall stud compression stresses. So this is the first part of the table, and you see the different loading conditions. We've got up to 70-pound ground snow loads in this table. Let's jump to the next page, which is the example that we'll want to look at from the commentary. So table 2.9b, and this is for a roof ceiling and 2 clear span floors. We're looking at stud spacing of 12 inches on center, a 2x6, 50-pound per square foot ground snow load, and a 36-foot building width. Gives us 338 psi of induced compression stress on our studs. So how we get to that number is about load factoring. So we'll talk about our loads and load combinations and load duration factors in just a second. Then you would take that tabulated compression stress and make sure it doesn't exceed your allowable. So that helps with the design process as well. So this gives you a sense, and again we'd have to jump to table 211, which we'll look at here in a second, to figure out the loads on the walls. But then this calculation here on the right shows how we calculate that compression stress. FC equals P over A, pretty straightforward calculation there. So we jump then to table 211, and that gives us our load-bearing wall loads from snow or live, and this could be for wall studs, headers, and girders. So we're looking at wall studs today. Let's jump down here to the bottom of the page, look at a two-story building, or a three-story building, sorry, with 2 floors. So we're carrying a two clear span floors and a roof with a 30-pound per square foot ground snow load, a 36-foot roof span, and that gives us a unit load of 2,442 pounds per linear foot. So the footnotes here talk about the load combinations. So I'll jump to the commentary so you can see those load combinations, how we come up with those loads. And so you see load combinations 1 through 5 here. You're going to see those again in the example we're going to look at in just a second. But I want to make sure you note here, and I made myself a note so that you remember that the load duration factor shown here on this right-hand column does not apply to modulus of elasticity or compression perpendicular to the grain. So that's important when we start looking at how we analyze these studs, because you can't just look at the load combinations and guess which one controls, because we're not applying the load duration factor to E, and the load duration factor is going to vary depending on the load combination. And when Lori shows you that in a little bit, you're going to see very vividly why this is important. So again, this commentary just works through how we sum moments around the building. We talk about here in this part of the commentary about balanced versus unbalanced snow loads, and for building widths greater than 40 feet, it's a more complex unbalanced snow load analysis, but we're within the limits here in this particular example that we're looking at. And so our snow load, our unbalanced snow load governs in this case, and so we come up with that 2442 for that particular load combination. And then the note here at the bottom talks about how you can change your load duration factor depending on what is controlling for your particular situation. So the tables are set up in a way to be very flexible, to help you with the the design process, kind of give you some tabulated values that may alleviate the need to calculate so many numbers all the time for pretty straightforward cases. This paper then talks a little bit more about the balanced and unbalanced snow load conditions if you're interested in some more background there. So I flew through that. I know I'm going to ask Marcy to come back and see if she can help us out with this next poll question.
Absolutely. All right. So studs should be checked for either main wind forced resisting systems component and cladding, main wind forced resisting systems or component and cladding wind loads, but not both. So go ahead and vote. Got about 40% of you have voted already. I'm going to give it about another 5 seconds. I apologize for such short turnaround, but we've got a lot of information to cover in a short amount of time. And I'm going to go ahead and close and share it. So we have 75% have voted false and 25% have voted true. And the real answer is, buddy?
The answer is false. So we probably have some new folks with us today, and we're glad for that because it gives us a chance to talk about this. And we've already got a question I see that came in about, what assumption or what code path is allowing you to make this assumption, where we're going to check main wind force and gravity, and then we're going to check CNC alone. And that's actually from the commentary to ASCE 710. That comes from an interpretation from the ASCE 7 wind loads task group that came up with these provisions. This applies to studs and trusses or truss panels between truss points with truss design and stud design. And so that's the code path. It's been around for quite some time, quite a few decades actually, and we're just continuing to try and get the word out about this information. So glad you're with us to learn about this today, and we'll continue to reinforce that throughout the presentation. So now I'm going to jump to the prescriptive design limits of the wood frame construction manual. And so here I want to point out, and this table is at the front end of Chapter 3 of the Wood Frame Construction Manual, the big difference here in this table is the load-bearing wall height limit of 10 feet. So in the IRC, we have a limit on load-bearing walls of 10 feet. And as we look at the tables here in a second, we carry that assumption forward into these prescriptive requirements. So once you exceed a 10-foot load-bearing wall height, then that's a very, I guess, a good simple definition for a tall wood stud. So a tall wood stud is a stud, a load-bearing stud greater than 10 feet, which is covered in the prescriptive requirements of the code. And you can see the non-load-bearing requirements still go up to 20 feet. So here's the enabling language in Chapter 3 that talks about the tables in Chapter 3 that we'll look at, tables 320A through B. Again, these tables are only going to analyze or tabulate CNC loads, CNC bending loads, because the checks that we've done indicate that the combined axial and main wind force loads don't control. So we're in the workbook now, and the workbook has an example of a two-story structure, and here is the isometric of that two-story structure. And we've got this front door and front window, and we've got studs on either side of the front door and window. We've got an attic, a habitable attic up here above, and so we're going to design these studs here, these tall studs on either side of the door and window, for a combined wind and gravity load, and see what controls. So we get to the layout of the building here, and in the example problem that we put together, here on the first floor you see a plant shelf over that front door. We put that in to show a platform frame for the workbook, and then that carries over into the second floor of the analysis. So this workbook actually only shows 9-foot wall studs. So we've got these 9-foot wall heights, roof pitch of 712, a 32-foot building width, and so in the workbook that you download, you're not designing a tall stud. So we've gotten questions before, well, what if we need to design for the tall studs? What if we take that plant shelf out? So that's what we're going to get to, but I just want to lay the background for you here, give you the context of this. So our wind load for this example is 160 miles per hour. Our ground snow load is 30 pounds per square foot. Our live load's 20 pounds per square foot. I think we've got an attic floor live load of 30. I didn't highlight that, so let me do that here for you. 30 pound per square foot attic floor live load. Then our deflection limits per this table in the IRC end up being H over 180 because we've got an interior gypsum board finish. So footnote D of this table is, whoops, sorry about that. Footnote D is what you want to look at to come up with that H over 180 deflection limit. So can we design a non-load bearing wood stud for the gable end and balloon frame that up from the top of the second floor to the ridge? And the answer is yes, by using tables 320A or actually 320B1, which I'll show you here in a second. We can actually balloon frame a non-load bearing stud with this CNC load up to the height of 18.3 feet. So we see down here in the table for W4.5 that we can get a number 2 2x6 Doug fir larch at 12 inches on center to work. Hem-fir actually doesn't work, so we'd have to double that one up maybe there at that ridge location if we decided to balloon frame that. Southern pine and spruce pine fir both work with that number 2 grade. I'm going to skip over this other assumption here at the bottom, which would be if we wanted to have an intermediate framing element. So how do we get that? Well, this is that table 320B1, and this is for both exterior load bearing and non-load bearing studs. You see the H over 180 deflection limit. We've got 3/8 wood structural panels on the exterior. If we come down here under 160 2x6, we see that 19-foot 5 for Doug fir larch number 2. We see the 18-foot height for hem-fir, and so that doesn't work. Spruce pine fir and southern pine both work at 18.5 feet. So at 12 inches on center, we can get that to work. Probably not as efficient as we could be, but we see at 16 inches on center, it just doesn't work. Those CNC loads are too high for that 2x6 in this case. Always got to pay attention to the footnotes. In table 320B talks again about interior zone loads. So we've calculated these studs based on those interior zones. If you want to calculate your end zones, then we'd have to probably drop that stud spacing down a little bit. In this case, since we're on a gable end, those studs are already shortened up by the time you get to the wall, the side wall, so they'll work. They go down to about 9 feet at that end. But if you're looking at a load-bearing wall, just know about these load assumptions. Now here's where the IRC kicks in. Table 320C says that we're going to limit the stud height based on gravity loads. And for the 2x6 that we're looking at, a non-load bearing stud is going to be limited to 20 feet and 24 inches on center per the IRC. So that's an overriding limit for these load bearing wall studs for gravity loads per the IRC. So chapter 3, prescriptive, that's where that limit kicks in. I'm actually going to skip over these two examples. This just shows you how we design the load-bearing studs at 10 feet. Again, using component and cladding loads, because we're limited to 10 feet, we know that's going to work. So that was the second floor stud. 2x6s actually work for that. This is the first floor stud. For that example in the workbook, carrying a roof ceiling and 2 floors, and we see the 2x6s will also work for that, but we're going to run out of time, so you can go back and study this or go back to one of our series that we presented on the workbook and take a look at the webinar that we did where we went through this example in much more detail. So let's get to this next poll question, and I'll ask Marcy to come on back.
Absolutely. So we've got out-of-plane bending does not need to be checked in stud designs if wood structural panel sheathing is applied to the studs. Is that true or false? So again, just a quick poll to check if you're listening. So, but these look like they're kind of tough questions for you. So
yeah, we've heard before that our
designed them that way.
That's right.
I'm sorry.
Our comments that came back said our questions were too easy, so we had to try and make them a little harder.
Right. So, all right, so it's been about 30 seconds, so I'm going to go ahead and close and then share that answer. So we've got 64% say false and 36% say true. And Buddy, what's the real answer?
The answer is false. And you'd have to go back to the table that we looked at earlier where we checked the CNC bending loads on the studs, and it actually showed 3/8" wood structural panels on those studs in the table that we checked. Now you do get some benefit for composite action on those studs that we'll talk about in a little bit, but you still need to check the bending capacity even if you have wood structural panels on there. So let's plow ahead, get into the example, and have Lori join us here in a second to go through this. So we're going to take that plant shelf out, and we're going to balloon frame that front window or the studs around that front window and door up 19 feet. And so we're going to be carrying the attic, ceiling, and roof loads there. So you see the loads that are showing up here. Dead live, ground snow load of 30, our attic dead and live loads there, 15 and 30. Our stud spacing 16 inches on center, and we've got wood structural panels on the exterior, 1/2" gypsum on the interior. And so we're going to use MathCAD to run through this example, and we have to iterate to do this. So we're going to be looking at number 2, Southern Pine, for our example, and because we iterated through here and found out already that deflection controls, and we're going to have to go with 2x8s, you're going to see that we use 2x8, so you see the B equal 1.5, D equals 7 1/4. So then we see the C sub R factor equal to 1.25. That actually comes from our wind and seismic standard. It's also in the background calculations of the wood frame construction manual, but this goes above and beyond the 1.15 repetitive member factor in the NDS and accounts for composite action on the studs if they're sheathed with wood structural panels on the exterior and gypsum on the interior. So if you want to learn a little bit more about that, take a look at the commentary to the wind and seismic standard. Recall we've got a 19-foot stud length, 32-foot building width, 2-foot overhangs. So we calculate our dead loads here based on our 16-foot spans. So we got 8 feet of tributary area. We come up with an attic live load of 240 pounds per linear foot. Our roof live load is 320 pounds, and our total dead's 280. Dead loads are earthquake loads, and rain loads are 0, so we're going to skip over those in the analysis. Our snow load that we mentioned earlier, we're going to look at both balanced and unbalanced. So we've done that analysis here on this page, and unbalanced controls, it's at 360 pounds per linear foot. So again, we're kind of flying through this, but it's going to be better for you to see the overall principles here than to really get into the nitty-gritty of the details. So you can go back and study this. We're going to look at main wind force wind loads, and using the envelope procedure in Chapter 28 of ASCE 710, we're going to calculate a velocity pressure with our main wind force of 23 pounds per square foot. Now, if you were to compare this to the wood frame construction manual, at a mean roof height of 33 feet, you're going to come up with 24 pounds per square foot. Since our building mean roof height is 25 feet, we're able to, since it's MathCAD and we can set that roof height, we can knock that down a little bit. So our velocity pressure is a little bit lower. And again, we've already incorporated the 0.6 factor here, you see in the velocity pressure calculation, to get us to allowable stress design. So now we're going to take a look at our main wind force roof pressure coefficients. And we're going to look at both perpendicular to ridge and parallel to ridge. So load case A is perp to ridge, load case B is perpendicular to ridge. So we're going to take our pressure coefficients out of ASCE 7 accordingly, and we're going to look at load cases A and B, and we're going to sum the overturning moments about the top of the leeward wall to determine the controlling reaction used in the design. So we're calculating our uplift loads here, And as it turns out, load case B controls and gives us an uplift load of 358 pounds per linear foot. And we're going to see in load combination 7 in a little bit, that's going to be offset by the dead load. So again, if we're comparing that to the wood frame construction manual, table 2.2a, and we interpolate, we're going to come up with a little bit higher load there, 391 pounds per linear foot. But that's because in the wood frame construction manual, we're assuming a worst case 20-degree roof slope. So that bumps our uplift load up to 391 pounds. Again, we're using MathCAD. We can sharpen our pencil and come up with the exact roof slope, in this case 7 and 12, and have a more exact calculation. So then our out-of-plane main wind force pressures, as we calculate through that to come up with the pressure on the wall and with our pressure coefficients using our velocity pressure that we calculated earlier, gives us 17 pounds per square foot. So when Lori compares that in a second to the CNC load, you're going to see a dramatic difference. So keep that pressure 17 pounds per square foot in mind as she picks up here and takes us the rest of the way through the example. Lori?
All right. Okay, there we go. Should be seeing my screen now.
Yes, you are.
All right, great. So thank you, Buddy. So Buddy talked about how we're calculating the calculations that were done for our various loads. So from here, let's talk about the combinations. So we used the ASD load combinations that were out of ASCE 710. And with designing wood in ASD comes load duration factors, and we do know that they will vary depending upon the kind of load that's included in the combination. So you can see for the various load combinations included in ASCE 7 in these square brackets, we've indicated which load duration factor would apply for that specific combination. And you can see in some of the combinations, for example, combinations 3 and 4, where we have some different options for, you know, live roof or snow. We've broken those down into 3A and 3B just so we can differentiate it in the calculation process, and also to point out to you folks that there is, again, a difference in the load duration when comparing a live roof load to a snow load, for example. We do get a lot of questions about the dead load offset for overturning, as Buddy alluded to. We check combination number 7. That's our that would include the dead load offset for overturning loads. So, and again, rain and earthquake are equal to 0, so we didn't include those in any of our arrays that were used to calculate the loads. So you can see, let me see. As you can see here, in this array, this is the array that we use to develop the values for the load combinations, and because of how MathCAD works, we've got the array numbered here, and you can see below it that we've got a key that tells you which load combination corresponds with which term in the array. So load combinations 1 through 4 are gravity load combinations only, and we're going to go ahead and check all of those combinations individually because, as Buddy mentioned, it's very tough to gut check those. You may just say, oh, number 4, the value in cell 4 might control for these units, for these members, because it's one of the higher values. But we don't know because that load duration effect isn't always apparent right away. So we want to check all of them for the gravity ones. When we get to load combinations 5, 6, and 7, those are all going to have a load duration of 1.6. So for those, we can actually just look at them and base the calculations on the value that was that is reflected in the combination. Now we're gonna get further into this, and you're gonna see that we checked load combination 6A as our wind load value, so that's going to be right here in number 8 in the array. So that's 462 PLF, and you'll say, well, why didn't you choose 6B, which was 730 PLF? We already checked that up here in load combination 4B. You'll see that it had an equal value, and load combination 4B actually does not have the benefit of that higher load duration factor, so it's actually a more severe load case. So we didn't opt to check load combination 6B. We chose 6A in this case. And this just is relaying what I just mentioned there. So getting into the analysis and how the load combinations were individually analyzed, we'll start with combinations 1 through 4. So we've got a 16-inch stud spacing, and we're assuming that the studs are resisting the gravity loads as well as the out-of-plane main wind force resisting system loads. So starting with load combination 1, which is a dead load only combination, we see that we can calculate the axial compressive force based on load combination 1 here. It's just based on our 16-inch spacing, and then this number PDIST1 is the value that's pulled out of our calculation array. Again, our load duration for a dead load only case would be 0.9. And then we calculate this F sub C1 star value. So this is going to be the reference compressive design value for load combination 1, and it includes all of the adjustment factors with the exception of the column stability factor. So we will use this F sub C1 star value in the calculation of that column stability factor. So we're going to do that next. We assume a pin-pin connection for our column, and we've got buckling about the strong axis, so we denote that with this subscript 1, since we have a laterally unsupported axis. We don't have to check the buckling about the weak axis because we've got the gypsum wallboard bracing, and if you check in NDS Appendix A, A11.3, you'll see that we don't have to consider buckling in the weak axis because of the support from the gypsum wallboard. So our effective length now is 228 inches, and we can calculate then our F sub CE value that's used also in the calculation of the column stability factor. So we'll scroll down here, and you can see our column stability factor for load combination 1, so C sub P1, is 0.319. So now we will use that to calculate the allowable compressive stress that can be applied to this stud. So this F sub C prime 1 is the allowable stress for the stud in load case 1. And we get an adjusted value of 388 PSI here. Comparing that to the applied stress, this little f sub C1, that's our applied stress in load case 1. You see we have our applied to allowable ratio is 0.09. So it is very low. It's not common that dead load would be controlled for a wood-based design, but it isn't impossible. So it is important to check this combination because there are some instances where it could control. Now going back to our other load combinations, these are all going to be calculated in pretty much the exact same fashion. So the only things that will change will be the subscripts that denote we're working with a different load combinations. So for example, this P sub 2 is our compressive force for load combination 2, which is just dead plus floor live. Our load duration factor in this case would be 1.0. Again, our calculation of our compressive stresses will be the same as before. The only difference would be we'd have a different load duration, obviously. Our controlling our effective length would be the same as well. So we go down, our column stability factor calculates to 0.29. So our adjusted compressive design value, our allowable stress, is this F sub C prime 2, 392 psi. We find our actual compressive stress to be 64 psi, and we're less than 1 again. We're at 0.16 with our ratio here. All right, load combination 3A, so this will be the dead plus the roof live load. We've, again, calculated our compressive axial force in the same way. Our load duration on a roof live load is 1.25, so that the values then would be calculated again similarly. Right, and then we scroll down, and our load duration factor, our column stability factor rather is 0.237, and we can calculate our allowable compressive stress here as 399 psi. Our actual stress is 74 psi, and again our ratio of actual to allowable is less than 1. All right, this is load combination 3B, so this is dead plus snow. Same calculation for the axial force. Our load duration factor, C sub D 3B, is 1.15 for the snow. So going down, our column stability factor then calculates out to 0.255, and we can see that our compressive design stress would be 397 psi. Our actual applied stress is 78 psi again, so we're at 0.2. Load combination 4A, we've got dead plus 0.75 live plus 0.75 of the live roof. So our load duration for this would be 1.25 due to that roof live load. And we can calculate again our column stability factor of 0.237, and our compressive design stress is calculated again at 399 psi. So with our applied stress of 86 psi, we have a ratio of 0.22 for our applied over our allowable. Load combination 4B, this is where we, instead of that live roof, we now have dead plus 0.75 floor live plus 0.75 snow. So this one will have our load duration of 1.15. And our column stability is 0.255. So we get down here and we find that our applied over our allowable is 0.23. So comparing all of those gravity load combinations, we see that load combination 4B was the one that actually was put the most stress on the stud in the gravity loads. All right, so now we need to get into our wind, our load case 6 for our wind. So we did have a slight omission on your guys' notes, so I do want to point this out. In the heading for this section, we neglected to include this 0.75 snow. It is included in the calculations, so if you guys want to just make a note in the heading there to correct your notes, that's a slight error on our part. We apologize. Again, the compressive load is calculated the same way, right? So this time, though, we are also including a wind load. So there is an axial component to the wind load, but then there's also going to be a bending component to the wind load that we're going to need to check. And this is going to be from the main wind force resisting system loads. So for a wind load, we find a load duration factor of 1.6 would apply. And again, the column stability factor calculation is not going to change. We see a value of 0.188. So when we calculate our allowable design stress, we get a value of 405 psi as compared to our compressive stress, which is 57 psi. So that is only for the gravity loads as well as the axial component of the wind load. So we need to check now the bending stress that is also going to be induced by those out-of-plane main wind force resisting system wind pressures. So we had that 0.75 multiplier in the load combination, so we apply that here, and we get our wind pressure to be 17.31 pounds per lineal foot. And then we also can calculate our bending moment based on that applied pressure. So now we need to calculate the beam stability factor, the C sub L value for this stud. We go into the NDS and we can determine that we meet the requirements in the NDS in section 4412 that will allow us to assume a C sub L of 1.0. So we don't have to actually calculate it. We can just use 1.0, so that is good for our analyses. Now when we compare the actual bending stress to the allowable bending stress, or the adjusted bending design values, we see that our applied bending stress from our wind load is 713 psi, and our allowable bending stress is 1,850 psi. So again, we are under 1, but because this combination has combined bending and axial compression, we need to do the interaction check that's specified in the NDS, and this is specified in NDS 3.9-3. You can see the interaction equation that would check that, and we get a value of 0.46. So we're less than 1 again, so that's good. All right, so now we've calculated our main wind force resisting system load. Now we need to check the adequacy of the component, or of the framing for the component and cladding load. So again, for a wind load, we would have a load duration factor, a C sub D, of 1.6. And you guys can, this is all just the ASCE 7 material on how to calculate components and cladding. None of that's different, so I won't get into that too much. But you'll see we calculate our component and cladding pressure as 25.48 PSF. So when we apply that for our 16-inch on-center stud, we see that we've got a load from our component and cladding pressure of 34 PLF. That's nearly double the main wind force resisting system pressures that we calculated as 17.3 PLF. Again, our bending design value, we calculate that is 1,850 PSI. So this is just comparing the bending stress only from the component and cladding load to the capacity. So you see we had our ratio of our applied to our allowable for the component and cladding loads is actually 0.76. The highest one we had before was 0.46. That was our interaction equation with the combined main wind force and the gravity loading. So you can see that the component and cladding is often going to control for your strength calculations. We ran a couple iterations of this with some different values for snow, and we came up that the component and cladding was controlling for various different snow loads as well. So with this 160 mile/hour wind speed, your CNC loads can be very substantial. All right, so the last thing that we need to check is our deflection. And I think Buddy had briefly alluded to this, that we did originally run this example with a 2x6 stud, and the stress ratios for the load cases we checked were all less than 1, but where it failed was in this deflection in the component and cladding load. So you can see our deflection, we had an L over 180 or H over 180 span to deflection ratio limit, and we've gotten it to calculate to L over D of 273. So when we tried this with a 2x6, we couldn't get L over 180 to even come close to working on those deflections. So, you know, that's a really important point, is to check your deflections, especially if you have some sort of brittle finish. You know, that can be a very big driving factor in your design. So I think we're, in the interest of time, we're gonna skip our last poll question. But for those of you guys that are playing along at home, I'll give you the answer. It is 1.6, it's E. So with that, I think we can turn it over to Marcy for some wrap-up, and then Buddy and I are going to come back with some questions. We do want to encourage everybody to stay on for the Q&A, especially if you did join us late. You need to be here for 54 minutes of our hour, so the Q&A will be included in that 54 minutes.
Okay.
Right.
I wanted to make sure that I had unmuted myself. I did.
Right.
All right, and let me get the screen back here. Okay. All right, sorry about the scrolling there. All right, so thanks, Lori and Buddy, and I have just some quick information. Our partner organization WoodWorks provides wood project assistance and other resources. If you want to reach out to them, email help@woodworks.org or visit their website. And the information is right here. You can also request assistance from them on our survey that we're going to be sending out shortly after the webinar today. We also here at AWC provide help with design professionals to stay informed about technical issues affecting the wood industry. We offer that design professional membership. That is a paid membership. There are lots of benefits, including discounts on publications. Check out www.awc.org membership if you're interested. And then for code officials, we have this Code Official Connections benefits. This is a special program for qualifying code officials. There are lots of benefits associated with this program that are just slightly different from the DPM, but this is a complimentary program for code officials. Let me go to the next slide. And here we go. As I said before, keep an eye out for an email from AWC within the next half hour or so. Complete the survey for a chance to win a free publication. Check out the information about your certificate of completion and CEUs, but note that the actual certificates will not be available today. They'll be available within 2 weeks. Remember that in order to receive credit, you must have been present for 90% of today. That's 54 minutes, so stay on until the end of the question and answers. Please join us again on July 13th for our next webinar on fire protection during construction. And if you have any other questions or want more information, just email us at education@awc.org or visit us at www.awc.org. Again, thank you once again for your attention, and now I'm going to give you back to Buddy and Lori for some question and answers.
And I believe Michelle has been screening some of the questions as well. So we're going to ask Michelle to come on and help us with some questions too. Michelle, I think you've got a couple lined up.
Yes, I do. And thanks, Buddy. Couple questions. Well, there have been a lot of questions related to the components in cladding and the main wind force resisting systems and the application of combining the loads, et cetera, et cetera. Is there a reference to go to get more information?
Yeah, and I know I went fast through this, so I'm going to show this page 20 of your handout. If you have those, gives a little bit more of a definition here. The CNC wind pressures obviously are much higher. And so there have been many discussions about how we define components and cladding in the roof structure. So first, here in the commentary to the wood frame construction manual, table 2.9a, we show the what we've been stating throughout, that we're going to check CNC alone, and then we're going to check bending from main wind force in combination with axial. And then we link to this paper, and I'm going to jump there because I pulled that up while we were while Lori was teaching, and talk a little bit about those CNC versus main wind force loads. So here's a link to that paper, and the last couple of sentences here on this page talk about the fact that the components in cladding are defined as elements that do not qualify as part of the main wind force system. They are either directly loaded by the wind or receive wind loads originating at relatively close locations, which then transfer to the main wind force system. And then some of the elements, such as roof trusses, load-bearing studs, and structural sheathing, have been identified in both systems. So that's where we get the suggestion and the suggested interpretation to design these elements that they would receive as part of the main wind force, and then separately as part of the CNC loads. So that was one of the questions that I saw. We're not going to combine main wind force and CNC loads to design these elements. We're looking at those two wind loads separately. But when we're designing for combined bending and axial, the interpretation from the ASCE 7 wind loads committee is that we use the main wind force loads. I was going to go to ASCE 7 commentary this week to try and dig that out, and we had some problems here with our office being closed for a couple of days, so I didn't get to do that. So what we'll try and do is find that reference and email that out to folks who have, who have been part of this webinar. So Michelle, do you have a follow-up question?
Yeah, it had to do with the poll question. There was some confusion on the question because I think the page 29 is where it is, if you want.
Okay.
And it states stud should be checked for either main wind force resistance. Oh, you got it. But not both. But I believe you do check both load case. They're just not simultaneous.
That's correct. So I mean, we do check both, and that's why the answer is false. We're not checking for one or the other. We're checking for both. So that was the intent of the question there.
We're getting tricky in our questions.
I think you also had some questions for Lori as far as what the load combinations and that type of thing.
Yes. Lori, I have a question for you.
Yeah, I'm here.
Do you have a sense on when dead load might be the controlling load case?
Yeah, so that's it is not a common occurrence in wood when it could be a dead load controlled design, but one example of where you might encounter that would be if you're designing a permanent wood foundation. You can get some soil loads on the members of the foundation that can be rather substantial and can wind up controlling over the occupancy loads. So that's a great example where it's imperative to check all of the connections, or of all the combinations.
Yeah, and
right.
So what I'm showing here on my screen now that I think you're all seeing is the different load combinations and the load duration factors, and I know we had a lot of questions about this. So load duration is unique to wood, as many of you know, and is based on the shortest load in the combination. So there were some people asking, well, why not just take whatever load controls, and I'll go to the next page here, where we show the matrix, why not just take 730, that's the biggest load, and say that that's the controlling load, and go from there? Well, there are two answers to that question. One is that we have to look at the load duration factor for each one that's shortest in that load combination, and the other is that we don't apply load duration factor to E. We don't apply it to the modulus of elasticity or compression perp. And so I don't end up jumping around on you here, I want to just kind of go to this table that Lori showed earlier, where we looked at different gravity load combinations which all have different load duration factors. And it's not intuitive. If you look at 3B, 4A, and 4B here in this box, 0.2, 0.22, 0.23, I don't know that you can intuitively guess which one of those is going to control. And the reason they're so close is because of the different load duration factors that are used in those load combinations. Now these are pretty low because we're analyzing a 2x8. We mentioned that a 2x6 actually worked for the strength calculations, and if you looked at these with 2x6s, those ratios would be even higher. And so again, it's not, you can't just intuitively gut check your loads and say, well, that's the one that controls. And some designers will say, well, why can't I just take those load combinations and divide by the load duration factor, kind of divide it out, and guess, approach it that way? Well, again, it's because we don't apply that load duration factor to E, to modulus of elasticity. So when we're looking at buckling critical applications where you're going to include E in the analysis, that just would not work. So it's one of the things that we were excited about teaching in this webinar, was this influence of load duration on these various load combinations. So Michelle, what else you got for us?
Or is there any, if we have design criteria that goes beyond the wood frame construction manual, is there any resources available to designing tall walls?
No, there really aren't. That's why we put together this analysis, because we get that question a lot. But hopefully what you're seeing here with the wood frame construction manual tables, and if you look at the load combinations in your area and the wind loads that you have, you could maybe run some analysis and come to a comfort level that you can design a lot of your studs with these CNC loads, and that's going to control a majority of the time. Now, WoodWorks has software. The Canadian Wood Council develops WoodWorks software, so if you develop your loads from ASCE 7, your CNC loads, your main wind force loads, and your gravity loads, you could design your studs using the WoodWorks software or other software as well that would design a stud. But these CAD sheets, for example, aren't available out there to the general public just because of liability reasons.
Do we have time for one more question, or
we
do we
have time
need
for
to
a
close
couple?
it up?
No, let's go ahead for a couple more.
Okay. Should biaxial wall headers be analyzed in the same way as studs?
Yes. I could elaborate, but the answer is yes.
Easy enough question, but yes.
and we did a webinar a few months ago where we actually talked about, it might have been last month, I can't remember, where we talked about stud design. And so if you go back and look at that, you'll see that we made those same assumptions for headers.
Right. And that's available on our website under the e-courses.
Yep.
If anybody wants to.
I think
you don't happen to remember the...
No, I don't. But I think there was a question too about can we really get 20-foot studs?
Right.
Going to be straight and constructible? And I think if you check with your suppliers, you can determine that on your own for lumber studs. But obviously there are engineered products out there now, structural composite lumber, PSL, OSL, LSL, LVL products that are being used for lots of different applications. So I know that folks in the engineered wood products companies have those as well, and the same analysis then would apply for those products as well. You just have to get the design properties from the manufacturer.
Also, could you talk a little bit about the finger jointed being interchangeable?
Yep, so finger jointed lumber is also used out there and is interchangeable with solid sawn, so finger jointed lumber would also be an option. That's a great point, and would be available in those longer lengths. But let's just be clear with 2x4 studs, your L over D max for a 2x4 or for any column, your L over D max for permanent construction is 50. So the length, the limit on the 2x4, just because of the strong axis of 3.5 inches, is going to be about 14.5 feet. So you can't go more than 14.5 feet with a 2x4 stud just because of the L over D limit of 50.
Right, and anything about the adhesives that you want to?
For the finger jointed studs, if you are in a wall that requires a fire resistance rating, then you'll need to use a stud that has what's called an HRA, heat resistant adhesive, used for the finger joint. So fire rated assemblies would require an HRA adhesive or an HRA designation on the stud.
Yep, and we have an FAQ on our website too, if anybody wants to go and Google it.
Good point. So I think we probably ought to wrap up there. We're about 10 minutes past and want to respect your time. Lori takes a look at the questions that have come in, and we'll do our best to answer those. I'll take some time to try and dig into ASCE 7 to come up with that reference in the commentary. I think I did that before a while back, and I should have had that prepared today, so I apologize. But thank you all for joining us this month, and we'll hope to see you again next month for another one of our webinars. Have a great day.